Okay, we're going to continue on lecturing here. So last time we got into a good amount of sort of chapter 2, and we really talked a lot about measurements and how to properly take measurements, and really the uncertainty that's attached to measurements. So as we talked about, whenever you're taking any type of measurement, like we'll do today in lab, again, it is always important to take a look at the scale that you're dealing with. And as we talked about, you want to figure out, once again, sort of what the large markings represent. So again, on this scale here, if I drew it correctly, large markings should again be 1 centimeter. You also then want to count how many of the smaller markings you have between those large markings. And again, here, starting about here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That again means that basically each of the small markings in this case, as we saw, was going to be 0.1 of a centimeter. We can really just up front figure out how far we should take our reading to by taking the smallest marking and dividing it by 2. And that's going to give us plus or minus 0.05 centimeters. So really what this will tell you is when you do take a reading on a scale such as this, again, you should take it to the second decimal place. And that's because whenever we take any measurement, whatever it may be, there should always be certain numbers that everybody agrees upon. So 1.1, 2, 3, 4, and 5. And those are, again, are the certain numbers. Here we would have to make an estimate for that last part there. We usually sort of visualize it sort of equally broken up between those two dashes. So again, if you feel like it's maybe a little further than half, you might record something like a 6 and obviously the unit, that being our first uncertain number. And all those together, whenever you record all of the certain numbers plus the first uncertain number, are significant figures. So again, this would have 3 significant figures with the uncertainty here. You could include sort of that precision there as well, and you'll have some type of measurement that looks something like this. We also did talk about, obviously, significant figures, which is what you get when you take a measurement like that. Again, anything that is non-zero is going to be significant. Anything where we have zeros, it really does depend on sort of where the zero is or what type of zero. Any zeros at the beginning, which are sometimes called leading zeros, are not significant. So those would be any of these zeros, kind of like this. Once again, we always go left to right. We don't start counting our significant figures until we hit the very first non-zero number that would be there. There's also trap zeros or captive zeros, and those are significant. So if you had, again, something like this zero in the middle would be significant as it is trapped. And if you're counting your significant figures, you would start obviously with that number there and continue on to the right. The last zeros are the trailing zeros, and they could be significant or really not significant, depending on the situation. But what determines whether or not they are significant, again, is that decimal place. And if you do have a decimal place anywhere in the number, it will make those trailing zeros at the end significant. So again, here, if we had something like this, these zeros up front here will not be significant. A reminder that we do not count those as being significant, even though they come after the decimal point. And that's because we have not hit our first non-zero, which is right there. So that's where we should start counting our significant figures at 4. These at the end would then be significant because there is a decimal there in the number. Any questions on any of that stuff there we talked about last time? Okay. So I think this is sort of where we left off. We also talked about the idea, obviously, of measured numbers and exact numbers. A reminder that an exact number is really anything that is going to be counted. that you would count. You really wouldn't do any type of experimentation or measurement to figure out what you got going on there. So again, if I had these pins right here and I want to know how many I had, I'm just going to simply count how many I have. I'm not going to do any type of experiment to figure it out or anything like that. More commonly in chemistry, where we come across sort of exact numbers are things that are definitions. So if you have a English to English conversion, that's going to be an exact number. If you're doing any type of metric to metric conversion, that's going to be an exact number. If you do cross over, though, between sort of metric and English conversions, you do have to sort of look at the significant figures in those when you're doing calculations. Where that really will come into play is when you do calculations, exact numbers are considered to have pretty much as many significant figures as you want. And what that means is we sort of ignore those numbers when we're doing a bunch of calculations to help us figure out how much our answer should have in terms of significant figures. So the only case where you would have to sort of look at a definition, again, is sort of a metric to English crossover. That's not an exact sort of conversion along the way. So here, obviously, if we weighed somebody 155 pounds, that would be a measured number. If we have a basket that holds 8 apples, that would be something that would be more of an exact number. You obviously would just count how many apples you had in the basket. 1 kilogram is 1,000 grams. That's a metric to metric sort of conversion. So that would fall under the exact numbers. And here we're going to go from Colorado to Houston. That's 1,720 kilometers. So that would obviously be something that was a measured value and would have, in that case, 1720 would have how many significant figures? It would have 3 significant figures in this case, right? There's no decimal point written in that, so that 0 at the end would not be significant. Yeah. So let's talk a little bit about rounding. So obviously, when we give answers, we do want to round them. We do want to round them really to the proper number of significant figures. So normal rounding rules apply. If the first digit to be dropped is 4 or less, then the rest of the numbers pretty much just get dropped off. If it's 5 or above, we do round up. In the effort to get to the proper number of significant figures, sometimes people go a little crazy with the rounding, and you should not go crazy and do any extreme rounding. For example, if I have 13,333 and I want 2 significant figures, what is the answer? 13,000. How about 13? Which one has 2 significant figures? They both actually have 2 significant figures, yes. But there is a big difference, right, between 13 and 13,333. If I owed you $13,333 and said, I'll just give you 2 significant figures, here's $13, I'm probably not going to make it out the door, I imagine, or anything like that. Maybe I will. You look friendly. So we never want to do sort of extreme rounding, which sometimes happens a lot with people. They're so focused on getting the right number of sig figs, they start lopping off numbers just to get it down to the right sig figs and changing the meaning of the number. Obviously, 13,000 written that way has 2 significant figures, and it still has relatively the same meaning. Obviously, if I gave you $13,000, maybe you give me the $333 teacher discount, that'd be okay. But it's basically the same value. So you, again, never want to sort of change the meaning of a number by rounding. You also could have as well did a little something like this, right, as we've talked about. A little scientific notation, right? And when you write a number in scientific notation, all those numbers in front of the timestamp part, right, are significant. So that would also be 2 significant figures, and another way that you could do that. In terms of rounding in general, if you're doing multiple calculations in a row, you do not want to round usually too much until kind of the very end. So you should keep track of everything as you're doing your calculations, significant figures, and how far you should take it. You should also take it to a couple of digits. Some people will take it to a few digits. They call it sometimes a guard digit to prevent sort of rounding too much. The reason for that is, again, if you sort of do one step, get an answer, and you round it really a lot, and then you take that number, do another calculation, and get an answer around that one, and kind of continue that process. Every time you sort of round that number along the way in the middle of the calculation, you're probably moving yourself further and further away from the right answer. So it's a good idea to keep some digits. It's also a good idea not to round to the end, but you should keep track of everything as you go through your calculations. So obviously here, if we want to do a little rounding, this is 35.723. So our second significant figure is going to be there. We're going to round up in this case because we're going to look at that. So we should end up with a 36 in this case. Here, that is going to be our second significant figure. Once again, we would look at the 2 and we would drop it, and we'll end up with something like this. Should I put a decimal point at the end? I should not, because then it would have 4 significant figures, right? So again, we don't want to put that extra decimal point in there if we don't need it. Coming here, once again, none of these are significant. We start counting here, and that means that the 6 is actually our second significant figure. That's a 2 that's next door to it. So that'll get us 0.0026 liters. And lastly here, our second significant figure would be that 2 that's there, looking at the 8. So we would do a little rounding up there at 1.3 kilograms. Yeah. Any questions on that there? Okay. All right. So more importantly, obviously, as well as sort of like knowing how to count significant figures, is most of the time we will deal with significant figures in calculations, and we really want to make sure that we sort of do the calculation correctly and give the answer to the proper number of significant figures. So there's really sort of 2 sets of operations that we commonly will do. That is multiplying and dividing, and also adding and subtracting. So when we multiply and divide, what we are looking at is actually the significant figures, and whichever number has the least number of significant figures is how many significant figures your answer should have. So if you multiply or divide, you're looking at each of the numbers or all the numbers that you're going to be doing that with, and whichever one has the least amount of significant figures is what you should end up with in terms of the answer. So if you're going to take 1.20 and times it by 3.2, in terms of significant figures, this has 3. In terms of significant figures here, this has 2. And since we're multiplying here, the 2 wins. Our answer should have 2 significant figures in this particular case. So if we pump that into our calculator here, on our calculator, we would end up with something like 3.84. We would want to then go to there if we were done with the calculation at that point and end up at 3.8. So multiplying, dividing, you look at sig figs, you look at the least number of significant figures. When you add and subtract, it's a little bit different in a sense. You are still looking for the least number, but we're no longer looking at significant figures. We're actually looking at decimal places. So when you add and subtract, it is the least number of decimal places is how many decimal places your answer should have. So adding and subtracting, smallest, but number of decimal places, not significant figures, is what you're looking at. So if you're going to take something like 2.111 plus 1.30 plus 2.0. We'll try this without the calculator, see how we do. There we go, 2, 4, 5. There we go. So when we're looking at this particular case here, this guy has 3 decimal places. This guy has 2 decimal places. That guy has 1 decimal place. That means that we should end up actually at 1 decimal place, and we should end up with an answer of 5.4. 5.4 has 1 decimal place, but how many significant figures? 2. Yeah, so that could be important if you're going to take that number and then do some more math with it, right? Or some type of calculation with it. If I'm adding all these together, let's just say instead of this being 2.0, this was just 2. Yes, just like that. Smallest number of decimal places is the whole number. Yeah. So you would then take it to the whole number in that case. Yeah. It would happen to be something like that. The reason we go with the least in both of those is, frankly, your calculation is only as good as your crappiest measurement. And your crappiest measurement will have the least number of decimal places, right? And the least number of significant figures. So that's the one that really limits how good or bad sort of your calculation is kind of your worst measurement. So kind of like you're only as good as your weakest link, right? So you're only as good in terms of your measurement that you made of your kind of worst measurement that you have. Yeah.
Like what's it?
Yeah. It's a good. Yeah. So let's talk about that. It's a really good question. So let's also talk about maybe in multiple steps as well, that maybe you're doing multiple things together, right? So maybe you're doing a little bit of adding and also dividing. So if we had something, say like let's just say we're going to go 2.5 times 123. We're going to divide it by 4.004. Then maybe, hey, we're going to add it to 3.2 or something like that, right? So there's a lot going on at once, right? So the general rule to sort of answer your question in terms of if you're going to be doing multiple steps is, I would highly recommend, if you're maybe going to break up a calculation, you're going to do like the first step of the calculation and get the answer, and then take that answer and kind of continue on to do another calculation. And maybe you're going to take that answer and kind of continue on. That's sort of what we were talking about a second ago. You really don't want to round in that situation until the very end. So sometimes people, like I said, I personally will keep, if I write it down, I'll keep a few extra digits, if I got an answer in between, and then take that number and continue on with the calculation. And that's what's sometimes referred to as keeping guard digits. And sometimes people will, if they do a calculation and it's the first part of the calculation, let's just say they got something on their calculator, with a bunch of numbers, and they really technically at this point in the calculation should stop at the 2 or something like that. They'll put like a little line maybe over the 4 or something like that and kind of continue on with it and keep it stuff. I personally, when I do it, and this is the way I do it, I personally would, if I was going to write the answer down in that sort of intermediate step, I would take a few extra digits, not everything that I see on the calculator, right? But a few extra digits past where you need. And personally, in my calculator, I would keep all the digits, and then I would just continue on with the calculation, on the display, and just kind of, multiply by the next number, divide by the next number. And then you should keep track of it all the way through your calculation and really kind of clean it up at the end. That will avoid those really roundy steps where you'll be changing the number along the way. So that's really a good idea to do that. Yeah. Yeah, we're going to talk about sort of the order here in just a second on that one. So that's a general rule that you should really kind of follow when you're doing just basic calculations and stuff like that. Now, if we have something like this in terms of the orders of operation, in terms of math, right? If we were going to do, all these steps together, the first thing that we really would do first is the multiplication part, right? It's the part that's in the parentheses. So we would technically do the multiplication part. So technically here, right, we would have 2.5 times 123, and on my calculator, right, let's go up here, I got like 307.5, right? Now, technically speaking, at this point, if that was all I was doing, right, in this calculation, I should end up with what number? How many significant figures? Should end up with 2 significant figures, because first number is 2 significant figures, right? Second number is 3 significant figures. That means technically that 307.5 should be 2 significant figures, which if you strictly rounded right at this point, you would turn that into 310, right? Which is going to probably change your outcome at the end here, right? A little bit, because you're now rounding a little bit. So here, personally, I would not round, but I would still keep in my head, okay, that should be, like 2 significant figures going on. The next thing that we would do mathematically, right, is we would take what we got up here then and divide by what we got going down here. Now, since we're dividing, we're still going to be doing smallest number of significant figures. So although I'm going to probably continue my calculation with that number up there, that technically should be 2 significant figures, right? And we're going to divide it by a number that should be 4 significant figures, right? So at this point, when we get the result of that answer, we should still have really 2 significant figures happening at that point. So again, I'm personally not going to round that top number to 310 at this point. I'm going to take the 307.5 on my calculator. I'm going to divide it by 4.004. And when I get this number, once again, on my calculator, I get, you know, this giant number here. And again, I wouldn't, in a normal situation, probably write that giant number. Yeah. So this is where we're talking about guard digits. I know just from looking at the math that, you know, I should end up at like 2 significant figures at this point, right? So if I did want to do some type of rounding, right, 2 sig figs over here, maybe I want to keep this guy or maybe even keep this guy, right? And that's maybe what I should write down. But again, personally for me, I'm going to just kind of keep the whole number in my calculator, which is usually a pretty good idea to do. But if you do want to kind of write the number down, keep a couple of extra digits. I would not write down all the extra digits at this point. You know, I would keep a couple or so, and that's usually sufficient to kind of keep you going. So now that we have this number, which if we write down, you know, 76.79 or even 76.798, we still should be keeping our head at this point. We really should be shooting at 2 significant figures, right? And if you really want to at this point, we're going to be adding next, which means we should be going at decimal places. So here we would take all this numbers and, you know, maybe we'll keep the last one too. We will now add 3.2 to it. And once again, I'm still using the whole number in my calculator. I'm going to add 3.2. And this is going to give me on my calculator 79.998218. Again, obviously you would not write all those numbers down. So I'm just a digit or two. You should try not to round super extremely, but definitely you should keep track of everything that you're doing. And again, sort of clean it up at the end. And you'll be good in most cases. Again, there could be some exceptions, but in most cases you should be good that way. Yeah.
Broken down into like
Yeah.
round after like the multiplication and division, and then added that one.
Yeah.
For example, on the test, if it showed that work, but it wasn't your exact answer.
Yeah. So usually in most cases you'll be okay if it's just like a slight rounding, you know, sort of error, as long as you did it, I guess, to round it correctly. I guess I'll put it that way, you know. So like, for example, I personally don't round on anything until like the very end, but I do keep track of everything. And like I said, even when I'm punching into my calculator, I just keep all the number and just continue on with it and stuff like that. So you'll see over the semester, you know, you might punch into yours and maybe you round it a little bit and you'll have like a slightly different answer because you did a little bit of rounding. So in most cases you'll be okay in that situation, you know. Again, as long as it's not like, you know, I had 5 and you had like a weird rounding of like you ended up with 10 or something like that, a super extreme rounding difference or something like that. But it's a very small difference, you should be okay. But the goal is, again, you definitely want to keep track of it. If you need to write the number to kind of use it on with another one, you don't want to write the entire number that you see in your calculator, but you should keep a few digits if you're going to continue on with the calculation. Now, if you're going to end the calculation at that point, clearly you should round it up to whatever it should be at that point. Other questions? Okay. All right, so here's a few examples. A reminder as well in terms of your calculator. Again, your calculator does not always give you the answer to the proper number of digits, right? And you may have to do some rounding. So we do some of this math here. We got multiplication. So we're going to be looking at significant figures. So that is 3 significant figures. That is 2 significant figures. And in this case, that would mean that we should end up here with that 7. We are going to round up, which would be 9.4. Here we're dividing, which means that is 4 significant figures. That is 3 significant figures. That means our answer should end up at 3 significant figures. And here the 3rd significant figure would be the 8 in this case. Looking at the 2 that's next to it, we'll drop the rest of it. So 0.0758. Now we are adding. So once again, we're going to look at the decimal places. So that's 2 decimal places. That's 1 decimal place. That's 3 decimal places. That means we should end up here at 1 decimal place. And that's going to give us 29.1. Again, that has 1 decimal place. But again, if we were going to maybe use that another calculation that we need sig figs, remember it has 3 significant figures. So keep that in mind. Here we're going to subtract. So we got 4 decimal places and 1 decimal place, which means, again, this is really the one that limits how good our measurement is. So we can only go to 1 decimal place there. and we would round up based on that number that is next to it. Any questions on that there? All right, so let's talk a little bit about some more about units and some measurements, and we'll get into some conversions here. But as we talked about, I think last time, there are certain prefixes that we use, especially for metrics, and we do have to be able to kind of change these. And there are some here that does come up a lot. Again, kilo, mega, centi, milli, nano, and micro, so probably almost the whole table. Oddly deci, not so much, but in chemistry, but all those other ones do come up a lot. And there's different meanings here that you can use. These are more sort of decimal meaning of what each of these means. Oftentimes people will use this sort of scientific notation meaning of each of these prefixes. And I think we might have touched upon it earlier on, but just to remind you that when you use any of these prefixes, which you should definitely know these guys, for sure for our class, kilo, centi, milli, and nano. Micro and mega, you'll probably see a little bit more in 1A and so forth, and maybe nano as well, but you should probably know this one. When we look at something like nano, which means in this case 10 to the minus 9. And basically what that means is that's really 1 times 10 to the minus 9. And the relationship of how it works, say if we wanted to go from nanometers to meters. In this case, there again is sort of a base unit and like a prefix unit. And in this case, the base unit is meters, right? So nanometers and meters. So meters is really the base unit of it. The nanometers is the prefix unit. So when you look at something like 10 to the minus 9, what that means is in one of the prefix units, that's how much of the base unit you have. So that means that in 1 nanometer, you got 10 to the minus 9 meters. And it's very common. People will always reverse those and do it the opposite way. That also means, for example, if we had centi here, which is 10 to the minus 2, if I had a centimeter and a meter in one of the prefix units, there would be 10 to the minus 2 meters is the correct way to do that. It doesn't matter the unit, the base unit. If I had a 1 centigram, that would be how many grams? 10 to the minus 2 grams, right? It doesn't really matter the base unit. The prefix works the same for all of them. Just like if I had 1 centiliter, that would be 10 to the minus 2 liters. So it works the same no matter what your unit it is. The prefix is always the same, but it's very common. People always want to go, for example, there's 10 to the minus 2 centimeters in 1 meter, and I'll do it backwards. So you want to make sure you always do that. Sometimes you'll see the larger version of these conversions, and again, they're just achieved by dividing both sides, for example, by 10 to the minus 2. That would get you your 100 centimeters is 1 meter. So they're both are perfectly fine sort of conversions, if you will. They both should give you the same answer if you punch them in correctly. But that is the correct way to use sort of that prefix one. Same thing with kilo is 10 to the 3. That would mean in 1 kilogram, there's 10 to the 3 grams. So that is how much there is in the base unit for one of the prefix units. Any questions on that there? Again, on your calculator, if you need to punch it in, if you have the like EE button or EXP button, you literally can just hit the E button and put like -9 without doing the 1. If you want to, you could also type it in as 1 exponent -9 on your calculator would be how you would punch it in your calculator. Any questions on those prefixes? So you should know these prefixes and how to go between them. Definitely the ones that are check mark, which is kind of like the whole table, basically, I guess. All right, so we talked about some of these conversions, and again, these are some length equalities. And equalities, by the way, right, are two things that represent the same amount of something, but they're on different units. So 100 centimeters is the same thing as 1 meter. 1 meter is the same thing as 1,000 millimeters, and there are 10 millimeters in a centimeter. So these are all length equalities. These are all some volume equalities, and again, this one is used a lot. And by the way, when we do have equalities, as we'll talk about, you could obviously write conversion factors for them. And conversion factors are really just fractions. So you could say in 1 liter, there's 1,000 milliliters, or in 1,000 milliliters, there is 1 liter. So you could do write some conversion factors that you could use to do some type of calculation if you needed to for these things. But that definitely is an equality that we use a lot. And really the other one that we saw, which is really a 1-to-1 relationship, is something that we use a lot. Again, a reminder that 1 milliliter is the same thing as 1 cubic centimeter. And they're both basically referring to a volume. As we see here in this one here is our cubic centimeter, and also our cc, which we don't use too much in chemistry but sometimes pops up a lot. All right, so we talked about the difference. I think remember that a cubic centimeter is usually achieved by taking 3 length measurements. So again, if you measured a cube in the length times the width times the height, and if you measured them all in centimeters, this gives you a volume measurement. And again, each of these individual measurements are length measurements. So typically, if you take any type of length value, cube it, it gives you a volume. And again, that's a way that you can basically figure out the volume of some type of solid object, like you'll do today with the cube. You're going to measure 3 different ways and get the volume of it. All right, and then a couple of mass ones that are important. Definitely these come up a lot. 1 kilogram is 1,000 grams, and 1 gram is 1,000 milligrams. Those are 2 conversions that we use a lot, so make sure that you kind of know those. All right, so we're going to kind of skip a couple of those. So let's talk about equalities and really writing conversion factors. As I mentioned a second ago, an equality, again, is basically 2 things that represent the same amount of something, but they're on different scales. So obviously, if you had $1, that's the same thing. If you had 100 pennies, right, it represents the same amount of money. You technically go through the drive-through and pay with both, right? Pennies are dollars, although they may put your sign up and not let you through the drive-through next time if you pay with all pennies. But you basically represents the same amount of money. And a conversion factor really is nothing more than a fraction. And the reason that we use conversion factors in chemistry here is really the way that they do want you to show calculations. So we talked about that as you go on to 1A and 1B, they want you to make sure that you show things the sort of proper way. And the proper way that we do calculations here in chemistry is through a process known as dimensional analysis. And dimensional analysis is an approach to calculations where if you have some type of conversion factor that comes from equality, like 2A equals 4B, right? And we'll just say those things are equal to each other. We could write 2 conversion factors of 2A over 4B, or 4B over 2A. These are our conversion factors. That's our equality, our conversion factors. So the process of sort of dimensional analysis is one where we set things up really in sort of fraction form. And it's basically opposites cancel each other out. So for example, if we had we'll go with 3A, and we want to know, how many B would we get out of that? We would start with 3A in our calculation. Although it is not written as a fraction, is thought of as being like on top. So it's over 1. So it's like thought of being on top. So when we go to our conversion factors, what we're looking for is basically the unit we want to get rid of to be in the opposite location. So A is on top. We would want to use the conversion factor here on the right-hand side. And that's going to put the A in the opposite location. So if we do that, we would set it up something like this, which is sort of how you need to show your work here. And in terms of units, what's going to happen is basically the A is going to be divided by the A, and they're going to cancel each other out. So it's the same thing if you had 2 on top and 2 on the bottom, that equals 1. They cancel each other out. So if you have the same unit on top and the same unit on the bottom, they basically cancel each other out to 1. Vice versa as well. If you needed to get rid of a unit on the bottom and then you need to put it on top, right? And it works the same way. So when we do this, what we're going to do mathematically is whatever is on top will be multiplied, and whatever's on the bottom here, you would come back and divide by. So in this case, we would take basically 4 times 3, which is 12, and divided by 2, which would give us 6. Now, the only unit that is left at this point is B, so this would be 6 of B. So this is a very simple sort of approach to dimensional analysis, but it all has to do with units. And you do need to show the units in the calculation, and you need to show how they cancel out by using conversion factors to do so. As you can see in this little example here, you will probably never use both conversion factors. You just need to use whichever one will get you to where you need to be. If you use both conversion factors, you pretty much will undo what you did, right? Because they're opposites of each other. So you typically will only use one conversion factor. Any questions on that? All right, so that's what we talked about with our penny here. So if we look at some common equalities, again, we have sort of the US or English version. We have our metric version, and we have our kind of crossover metric to US. So once again, each of these things here, we could write conversion factors for. We could say there are 1 foot, there is 12 inches, or in 12 inches, there is 1 foot. If we wanted to do something like this, we could say in 1 kilogram on top, there is 1,000 grams, or 1,000 grams is 1 kilogram. So you should know some of these here. Hopefully you know this one. Yes. The miles and feet is a very common one that comes across a lot in chemistry, so you should know that. Cups in a quart, that's a good one. These are some metric ones, which frankly you should know probably most of these that are on this list, so make sure you kind of know most of those in there. Metric to US, this is an exact conversion. They do want you to use a different conversion for pounds to grams. They do want you to do 1 pound is 453.6 grams. And here they will consider that an exact conversion as well. So that's one you should know for sure. And we'll go with it as an exact conversion. If you did use the 1 pound to 454 grams, that would not be an exact conversion. So when we're using any of these equalities that translate into conversion factors, again, if you pull anything from really this column, the English to English, as we talked about, is considered an exact number, which means we don't have to worry about it in calculations in terms of how many sig figs we should end up with. If we use metric to metric, you do not have to worry about it in terms of significant figures. But if you're going to pull something from sort of this column, you do have to sort of look at the significant figures in those conversion factors. So for example, if we were going to do, say, the 1 liter is 1.06 quarts, and we were going to use this as a conversion factor of like 1.06 quarts over 1 liter, we would look at the significant figures here when we're doing our calculation. We would clearly look at the numbers that are in the actual number, not the one that's 1. So you'll always have in a metric to English or any really conversion metric to English one, you'll have usually a 1 to some other number. So you obviously want to look at the other number. So if we were counting significant figures with that conversion factor, it would have 3 significant figures, which is the 1.06, is what you want to look at. Any questions on that? So for our purposes, they'd use the 1 inch is 2.54 centimeters as an exact conversion, which you don't have to worry about sig figs with that. And again, we will also use this for pounds to grams as an exact conversion. So you don't have to worry about significant figures on that one either. Obviously, time you should know, right? So I think we might have talked about it, but again, 60 seconds in a minute. Yeah, 60 minutes in an hour. And again, only 24 hours in a day, not 60. Yeah, so 24 hours in a day. It's a very common mistake people make. They go like 60 hours in a day. I think it's because they go 60, 60, and then they do 60 for the hours as they're doing that conversion. All right. So here's a couple, again, examples of how we can write our conversion factors and really just a fraction version here. 1 mile is 5,280 feet. Or we can use it as 1 mile is 5,280 feet on the bottom. So again, if we were going 35.5 miles and we want to know how many feet that is, we want to set it up dimensional analysis way. We will take our 35.5 miles. Our miles are up on top, so we need to go with miles in the opposite location to cancel out. That would be here. We have 1 mile is 5,280 feet. The miles on top and the miles on the bottom would cancel. We're going to multiply here. That's going to give us 35.5 times 5,280. Going to give us a 187,440 feet. First off, any questions on the setup? That is how you need to set up everything. Yes, with the units and this dimensional analysis approach. Let's talk sig figs. Yes, this conversion here, as we just saw, is right here. That's a English to English conversion, which means it's considered an exact number, which means in terms of sig figs, we're not going to worry about it, right? That means in most conversion problems, not 100% of the time, but in a lot of times, that very first number is where you should probably be looking. That first number has 3 significant figures. All we did in this case technically is multiply and divide, which means our answer should have the least number of significant figures, which means this guy should end up at 3 significant figures here at 187,000 feet. Yeah. Any questions on that? So again, that conversion factor, consider an exact number. We don't have to worry about it in our problem here. All right, some other conversion factors. 65 miles per hour. So if you have something in words, right, which is something per something, that's like a fraction, right? So basically we are driving 65 miles in 1 hour, or in 1 hour, it will take us 65 miles, or 1 hour we could go 65 miles basically. So again, we would use this as a conversion factor. Only one of them depending on that. So maybe if we had to go 2,000 miles, we want to know how long it'll take us, right? We could figure out if we were able to drive 65 miles all the way through, how many hours it would take us to get there. A gallon of gas costs $3.05 for 91. Okay, you know how old that slide is, maybe. Yeah, that actually was expensive when this slide was made. Now we would probably die for $3.91 in terms of that. But again, that's basically for every gallon of gas, you could pay $3.05, or $3.05 for every gallon. Now, other things that we oftentimes will come across are percentages. And when we do have percentages, we could turn them into really usable conversion factors. And whenever you're dealing with a percentage, right, the best way to sort of turn it into like a usable number is to assume you have how much of it? 100, right? And that basically will keep the numbers the same, right? So if you got like 50% on your exam, you probably got 50 out of 100, right? Hopefully not, but that is how that math would work. So if we have something that's given to us as a percentage, the best thing to do is assume you have 100 of it and turn it into a conversion factor. So for example, if I had 12% body fat by mass, well, we could do some metric sort of deal there. That would be 12 kilograms of body fat per 100 kilograms of body mass, or 100 kilograms of body mass per 12 kilograms of body mass. If we want to do more of the English sort of conversions, we could do 12 pounds per 100 pounds of body mass, or 100 pounds per 12 pounds. We could also, for example, if you had a solution that was 5.5% by mass sodium chloride, what that would mean is, in this case, You have 5.5 grams of sodium chloride and 100 grams of solution. Or again, you can use it in the opposite way. 100 grams of solution would have 5.5 grams of sodium chloride. The M/M means mass to mass percent, and that's how we know they're grams and grams is what we're talking about in terms of units. So very commonly in chemistry, we have things that are given to us in sort of percentages. We need to kind of convert those into usable sort of conversion factors. Again, assuming 100 is a good way to do that. Any questions on that there? All right, so as I mentioned before, dimensional analysis is pretty much how you are expected to show your work in this class, and then 1A and 1B as well, if you would like all the points. So once again, dimensional analysis is the use of conversion factors, it's the use of that sort of fraction system that we were just looking at. Again, you have a certain unit you do not want. You use a conversion factor where you put that unit you don't want on the bottom, and the unit that you are looking for goes up on top. Once again, you're then divide those guys out from each other, and that will leave you the unit that you want on top. Now, in some cases, you may have, like, for example, miles per gallon or something like that, or miles per hour. You may actually have 2 units in a number, right, that's given to you. And you may want to change both of those units. So maybe you want to know your speed from miles per hour to kilometers per second or something like that, right? So you may have a situation where you need to replace both of the units with other units. We still use dimensional analysis to do that. Again, we go opposites. So maybe there is a unit A to unit C. The unit A would cancel. And now at this point, I would have unit C over unit B. Now I need to get rid of B. I need to put unit B on top or bottom here. Unit B would need to go in the opposite location, which is up on top, right? And we'll just call this unit D, for example. That would cancel. And that would leave us some type of answer where it is unit C over basically unit D, whatever those units may be. Would be what you would end up with. So sometimes there are multiple units you got to change. The approach of dimensional analysis is just this. You can clearly see where all the units are. It makes the math easy for you. Once again, here in terms of the math, we would be multiplying by whatever's on top, and whatever's on the bottom we would be dividing by. The purpose of this is to make it easy to know what you should be doing in math. What happens with a lot of people when they do not set it up in dimensional analysis, besides the fact that you will not get full credit in this class or any of the chemistry classes you take here, when you just kind of randomly throw down numbers with units everywhere, I used to call it like the stacking approach. Like you got a number and you got some units over units, and then you're dividing units over units, and you're not really sure what you're doing there. People usually will divide when they should be multiplying when they should be dividing. And frankly, sometimes people have no idea like where the unit goes at all. Like, where does it end up? Is it on top? Is it on the bottom? So the purpose of this is to have a place where you could clearly see each of the units separately. And it's a very simple approach of, if you need to get rid of it, just go opposite with the same unit. So opposites always cancel. Pretty much in math, right? Opposites cancel everything, right? Move things to the opposite sides. That's like in math, if you have 2 numbers you are multiplying, right, on one side, but you want to bring it to the other side, you need to do the opposite thing, right? So multiplying, you need to divide, right? Just like if you had a number on this side and you wanted to bring this number to the other side, you're dividing, you need to multiply, right? So it's always opposites of math, right? Cancel things out. All right, so these are the general steps to problem solving and dimensional analysis. You should write what's given to the problem. So sometimes it's very helpful in a lot of chemistry problems, just in general, to write what's given to you in the problem, especially later on when we have formulas. It will oftentimes point you in the right direction in terms of what formula to choose. You want to write what you want to find. You want to think and write the appropriate equalities. You want to write the appropriate conversion factors. You want to set it up using dimensional analysis, and then you want to solve the problem. So again, here for full credit, you really do just need to show those last two steps. If it helps you to do all the other steps, you can do it. But you do need to show the dimensional analysis part with the setup and the units, and obviously the answer to the proper number of significant figures. But again, if the rest of the steps sort of help you, you can do that. So let's take a look maybe at one here. Obviously, this is a very simple one. We want to know how many pennies are in $3. And here, this would be our equality, which is $1 is 100 pennies, which will give us our two conversion factors that we could use. So once again, here we would start with our given, which is our $3. Once again, it's not written as a fraction, but the units of dollars are up on top, which means, again, we want to go opposite to get rid of it. So we're going to use that as our conversion factor, $1 on the bottom, 100 pennies up on top. The dollars will cancel. We are multiplying across the top and dividing by what's on the bottom. In this case, we're basically taking 3 times 100 divided by 1. Should give us 300 pennies. Any questions on that straightforward one there? All right, so let's try one here. Why don't you try this one? You go to the local AM/PM, little thirst oasis. You get 32 fluid ounce drink of Diet Coke. How many gallons did you drink? Here are some equalities. And again, here are some of the conversion factors that you could use. All right, so set up this problem using dimensional analysis. Okay, let's take a look at it. So this is given. This is what you want to find. These are the appropriate equalities and our conversion factors to come from it. So we're going to always start with what is given, which in this case is 32 fluid ounces. Once again, that is what we want to get rid of. So this is sort of our pathway that we chose. We're going to take fluid ounces to quarts and then quarts to gallons, which is what we're going to end up with here. So we do want to go opposite here, which means we want to use the conversion factor here on the left to do so. That would give me 1 quart on top and 32 fluid ounces on the bottom. At this point, if I stop the calculation, we would have fluid ounces that are canceling each other out. The units that we would be left with at this point is quarts, right? So that's close to what we want, but we do want to obviously take the next step to get us to gallons. So we'll use our second equality to do so. By setting it up like this dimensional analysis, we could clearly see that the quarts are up on top, which means to get rid of quarts, we need to put it on the bottom. So again, opposites to do so. So that is over here. So we can continue on here. And we would have 1 gallon up on top and 4 quarts on the bottom. Once again, the quarts on top and bottom will cancel each other out. At this point, we're going to multiply everything that is on the top. We're going to come back and divide by what's on the bottom. And if you do so, you will end up with 0.25 gallons in this case. Yes. Now let's talk about a couple of things. You do not end with 1/4 gallons because that makes me think you're just too lazy to divide. Yeah. So never give an answer in a fraction. Divide it out, get a number. And I say that because I've had people on exams and stuff write something like the answer is 446 miles per 3,250 hours, right? That's my answer. That answer is going to get one of those. Yeah. So don't do that. So make sure you divide it out and always give a number. Secondly, here, they technically want you at this school to do these type of calculations all in one sort of dimensional analysis sort of flow, if you will. You know, we could have technically stopped after the first part there, right? Got an answer and then took that answer to continue on and do the second part of the dimensional analysis conversion. Which if you want to do, I personally am okay with it, but some teachers down the road might not be okay with it. They kind of want you to kind of do it all together in one step. So if you do, this would be a situation like we were talking about earlier that you would not want to round too much there in the middle part. Not that there's a lot to round here, but you know, you would not want to round too much in that middle step. Significant figure wise here. We are going to be looking at two significant figures based off of that. The other two are pretty much exact numbers, so we don't have to worry about those. So we do end with two significant figures on our answer in this case. Any questions on that? So once again, if you want full credit on the whatever you're taking this on, this is 100% what you need to show, all like that. Again, if all this top part helps you, you could do it, but you don't necessarily have to show it or anything like that. So you just need to show the bottom part there with the setup and the answer and stuff like that. Any questions on that? All right, take a look at a couple more here. You got an antibiotic dose of 500 milligrams is ordered. If it comes as 250 milligrams per milliliter, how many milliliters would you be given? Conversion factors sort of written into the problem like we are here. It comes as 250 milligrams and 5 milliliters. So this is really a conversion factor. And once again, we could use it in sort of the opposite direction there. So we're going to start with what's given, which is 500 milligrams. Once again, not written as a fraction, but basically the milligrams are up on top, which means we actually do want to use that sort of conversion factor in this form so that it will be opposite. So we'll do 250 milligrams on the bottom and 5 milliliters up on top. Milligrams will cancel. This will end us with 10 milliliters in this particular case. Once again, we're going to multiply there, come back and divide there. First off, any questions on the setup here? Significant figure wise, right? We should look at a few things. So we should look at this original number, which has 3 significant figures. Should I look at this numbers? I actually should in this case. That's not like a true conversion, right? It's just specific for this problem. And in this particular case, that means the top number here has 2, right? Bottom number has 2 as well, which means really my answer should end up as 2 significant figures. Yeah. That is also why should I write 10.0 in this case? I should not, right? Because it will then be 3 significant figures, right? So by putting a decimal point at the end, keeps our sig fig. So in here, we got 2 significant figures. And since all we always do pretty much in dimensional analysis is multiply and divide, that would be the smallest number of significant figures that you would have. Any questions on that there? All right, so why don't you give this a go? Patient receives 5 pints of plasma. How many milliliters would that be? Here's a few equalities and conversions. So again, set it up using dimensional analysis and see what you come up with. Okay, let's take a look at this one. So we are starting with pints. We want to get to milliliters. So again, one pathway is pints to quarts, and then take our quarts to milliliters. Again, those are the conversion factors that you could use. So we're going to always start here again with what we are starting with that was given, which is 5 pints. We could see that it is on top the units. So we do want to go opposite to cancel. So we do want the pints on the bottom. So we would do 1 quart up on top and 2 pints on the bottom. At this point, again, if we stop the calculation, the units of pints will cancel each other out. We can now clearly see up on top, we have the units of quarts, which we want to get rid of. So again, opposite to do that would mean we need to put the quarts on the bottom. That means in this case, we will actually roll with that conversion factor there to do that. And continuing on here, quart on the bottom, 946 milliliters up on top, quart on top, quart on the bottom will cancel. That will leave only milliliters as the only unit that's still standing, which is good. We are again going to multiply across the top. So it's going to be 5 times 1 times 946. Make sure you hit equals. We're then going to come back and divide by what we got on the bottom, which in this case is just 2. It's going to give us 2365 here. Milliliters. First off, any question on the setup or the calculation? Should that be my answer in this case? It should not. We should look at some sig figs here, right? Do I have to be concerned with this number? I do, right? So that's 2 sig figs, right? Do I need to worry about this number? I don't. It's an exact. How about this conversion factor? You actually should, right? Because that's one of those metric to English. This has got 3, which means still the least number is 2, yeah? Which means something like 2400 milliliters here would be a right one. Or if you want to do scientific notation, 2.4 times 10 to the 3 milliliters would work as well. So again, this is a case where you do have to kind of look at the conversion factor there in the middle because it's metric to English. I will say not 100% of the time, but pretty close, pretty high 90s probably. If you're just doing conversions like this, usually that first number that you start with is pretty close to the right number of sig figs. And again, not 100% of the time, but pretty close, yeah.
Being like round up, if you're doing like an experiment, you're rounding up, but that means you'll reduce that positive the outcome of the
So again, it really still comes back to kind of the same idea. These are the rules that you should follow for significant figure calculation, but still it's really based on why we look at the least, because again, that is, in technically speaking, kind of like your worst measurement in a sense. And it's the one that really limits how good your answer is. So, you know, obviously we weren't able to say we're giving it like 5.0000 pints to start with, right? Which would give us a lot more significant figures at the end of the calculation and stuff like that. So because really that value a lot of times is sort of a measured value or the value that you're starting with, the one with the least is the one that really limits you. So you would still want to follow those rules. So obviously there is a difference, but it's really based on how good that first number is. Other questions? All right, let's try another one here. All right, you're stranded about 125 miles away from home. You decide, hey, it's only 120 degrees outside. Let's take a walk. And you walk an average of 55 feet per minute. How many days is it going to take you to get home? Yeah. All right, so see what you got going on there. A couple of conversions, yeah. Hopefully some of those you know. Yeah, let's take a look and see how we're doing since we're getting to the end here. In this case, we want to go a distance of 125 miles. This is really our rate at which we are walking, right? A rate's like how far you go in a certain amount of time. That's really what we're going to use to go really from distance, right, to time, which is ultimately what we're looking for, which is how many days. We do have a problem though. Our length measurements, if you will, are in different units, so they're not going to work like together. You have to either convert the miles to the feet, right? Or you got to do the feet to the miles, whichever way you want to do it. I am personally going to first take the miles to the feet, and then I'm going to use the rate as a conversion factor to basically take the feet to minutes, right? And then that's going to get me to time that I can then finish out the problem. So I'm going to start with the 125 miles. I'm going to use my equality here to use a conversion factor to get rid of miles. In this case, I want miles on the bottom so that they cancel, and that is opposite, and 5280 feet. Miles and miles would cancel. At this point, if I laid up a number, and if you got a number at this point, you got like something like 660,000, I would take the whole number and just continue on with the calculation. Again, I wouldn't do any type of sig figs or anything at that point. But we can't continue on with the calculation at this point. We want to get rid of feet and end up with time. We could use this rate that was given to us as feet per minute. Our minutes over 55 feet. So in this case, since feet are up on top, we would want to flip it around and use it in the opposite direction here. Again, so that they cancel. That would be 55 feet per minute. At this point, feet cancel. Again, the benefit of this is I can now clearly see that minutes are actually on top, which means get rid of minutes. I want to put them on the bottom. And we could use this if you like, 60 minutes. There is 1 hour. Minutes will cancel. And again, if I stopped at this point, I would be in units of hours, right? So I do need to go one more, 2 days. Again, our 24 days in an hour now, 24 hours in a day, which is good. 24 hours on the bottom, again, opposites, and 1 day. I have it now set up that I could clearly see where everything is. And I can't tell you how many people will do a problem like this and those 60 and 24 will end up on top and they're multiplying when they should be dividing and stuff like this. So this is the purpose of dimensional analysis. So you could clearly see where everything is. Once again, here, we're going to roll across the entire top here and multiply and come back and divide. And if you do all that, you're going to take 125, you're going to times it by 5280. By the way, hit equals at the end of the top there. Also, a mistake people make is they want to punch everything on the bottom in at once. Don't do that if you want the right answer. Divide by the first number, which is 55, hit equals. Divide by the next number, which is 60, hit equals. Divide by the next number, which is 24, and hit equals. And you will always get the right answer. If you try to punch it all in at once, there's probably a pretty good shot you're going to end up with the wrong answer. We're going to get 8.33333 days. And that's a lot of days, but that is how far we would go. Now let's talk about significant figures and where we should end up. We don't need to worry about this one, right? It's an exact number. We don't need to worry about this one. It's an exact number. We really don't need to worry about that one. It's an exact number. Do I need to worry about this one? I do. And although I didn't write it, it technically is 1 on top, which is not what we look at, but we would look at the bottom here, which is 3. And we would worry about this one, which is also 3. And that is why we ended up with 3 significant figures here at the end. Question on that? So once again, you do want to make sure that you show that bottom step. And that is the proper way to show your work in this type of class. All right, we'll lay it up there.